Okay, shall we start or?
Yeah, please start.
Yep, okay, sir. Okay, so I'll just share the screen. So we were trying to make an iPad design, okay? So just go to CMOS VLSI, go to pads, make X, and the ring can be 001, maybe I just try. All the values rest 1 because this is number of VDDVS's pair, okay? So it tells that how many number of size, okay. So he generates an iPad. And now we can just insert a NAND gate design. I just go to file, say insert layout, and select the NAND gate, any of the NAND gate which you guys have made earlier. So it'll come on the bottom right hand side. Generally on the bottom side it comes, and we can take the move option. Maybe I just change the color of the background to white. The refresh rate becomes faster. I just select that move option and place it somewhere on the center of it, okay, anywhere. So you can see in the center one there is a little bit of dot, so that indicates that that's my design. Okay, maybe I just bring it to this corner. Yeah, so here you can see this one. Oh, it's quite small. Okay, or shall we make something bigger which is easy to see? Okay. Okay, so what we have to do now is we have to connect this IOs of this NAND gate to this one. So you can see how big and small the design is. So our NAND gate is over here, right in the center. Small, looks like a small dot. And on the left hand side, these are the rings. Okay. So what I do is I double click and or maybe a single click, and I just see that which is this line. Okay. Okay, so this way, this one. Okay, so that's my IO pad on the left one. Okay, so I will assume that this is my input pad. Okay, this is input pad 1. So here you see that when you select this one and zoom out, zoom in, so you see that this uses a metal tool line to touch the pad. Okay, so what I will do, I will use the palette and use the same metal layer. Okay, use the same metal layer to connect with my design. Okay, so what I do, I just zoom out. Okay, and I take the metal 2 layer and maybe I just short it and come like this. So here you can see that this is extended one and it is shorting to this one only, because you can see that this is highlighted and the rest of them are not. Okay, now if you see this very closely, if I travel from this, or I hope you guys are able to see this. Yeah, so here you can see that this is the blue line on my mouse cursor, and I will travel till over here. I will take a lot amount of time, right? And by drawing manually, maybe I will take too many number of turns, although in this case it's very simple. Okay, but later you will find trouble in connecting manually. So there is another method possible. You can go to palette, say CMOS VLSI, and you just say that you want to generate a path. You have to use a path. Okay, so you can specify that what is the size of the metal width you want to use. So it's a 4 lambda. Which metal layer you want to use? So you say metal 2 because that's what you wanted to use. And do you want to add any path contacts at the end or not? So all this you can specify. Okay, so you can just say start path and left click over here, come to this side, and then end it over here. connect it twice and then escape whenever you want to. So here you can see that this path has been generated. Vertically is metal 1 and horizontal is metal 2. And if you just come to this point which was contact, so you can see this has been shorted. Okay, and over here so he has been using some metal layer to reach over here to make the end connect. I just take a tin gate and extend it over here and just right click and say connect layers. Okay, now I just use the second layer. The second one I can come from the bottom side. Or maybe I just zoom this area, the bottom one. Okay, why it has not connected? Yeah, there is an IO. There was an IO. I couldn't see because the zoom factor was very less. So I can see a vertical line coming up. So I just take electrical node information. So this is also again using a metal 2. So just to be safer, so I just go to this side. Okay. I take the palette and use metal 2 to slightly bring it out so that I can easily route laterwards with my path method. So here you can see that there is my NAND gate on the left hand side. So I just go to contacts. I'm a MOS generator. Paths, I just say the number of contacts, metal 2, this is a contact, I'm a path I have to make. So say start path and click on that node and vertically come somewhere over here. Click it twice. Okay. I think I press escape too early. So I just delete this path again and do it again. So I just say path, start path, and maybe I just go horizontally first. And then I come to vertical side. Yeah. Then I just take the electrical node and ask him to show me the highlight this. So the previous one was not deleted. I should delete the previous one and delete this one a little bit, and I zoom the area. So here you can see that this is my the path which was brought from the bottom side. I can just ask him to extend this a little bit. Yep. Then I just go to palette, select the tin gate, and maybe a little bit of extension, and stretch and move. Come over here, right click, connect layers. So this has been also shorted to the pad. Now I just verify that these are connected or not. So I take the electrical node and highlight this. So I should see the pad also highlighted. So pad is not highlighted because my horizontal path was not made properly over here. Something may have went wrong. No. The horizontal path was okay. These two were not connected. Okay. So you can see and understand that many number of stuff is coming up. That's okay. If you want to do this, then it's also okay. If you're not, then also okay. Because I just wanted to cover this to make you guys understand that how the IOs are being made and what difficulties are being faced. Because still the experiments, what you have done so far, they were quite basic one to start. Okay. I believe my voice is coming properly this time, and there are no much issues of the audio because there has been no comment or response coming up. So I thought to ask and confirm. Thank you, Tanmairam. Okay. And inputs are connected. Now I just need to connect the output to somewhere, and also the VCC VSS. So okay, so I just zoom, and this is the output I can make use of. So this is the pad which is I will make use of as an output node. So I just zoom in the area where it went. Okay, something went wrong. So you have to keep a little bit of patience because now things get very much bigger and steps need to handle properly. So I take the middle two layer and extend a little bit. Yeah. So this guy connects now. I'm just searching my area where I have to reach. Yeah. So this is the point where I have to reach from here. So again, I will go to path generator, contact, MOS generator, I mean like path, and say start path. So from here, I will just go horizontal. Okay. And then I will go vertical. That's it. So I will just zoom that area. It's far away again from the standards too. And still, it's okay. I just take metal one because I was using metal one for the output, and short it till here, and short it till here. And I just delete the contact and extend this, overlapping, and right click here and connect layers. So the output connects to the output node pad. So we can just verify this by clicking the electrical node and selecting the line you want to highlight. And the pad should be highlighted, but it's not highlighted. So that means somewhere connection issue was there. Okay, so this pad was not connected to the horizontal line. So here you can see that my start pad was slightly way up. So I just take the metal two layer and extend it. Yep, so this guy shorts, and I take the electrical node, click on this node, zoom out. The pad is highlighted and NAND gate is highlighted. So I ensure that these two are connected, okay? So ideally, like it's the same way I can connect the VDD supply, okay? But let's say I just go back, zoom the NAND gate, and I just apply the VDD and supply here just to be quick. So I take a VDD supply from here. Otherwise, it should have been from the pad I was. Because what happens when you draw a track till the pad, the RC values of the wire paths also accumulated on your loads. So that has to be checked and challenged, okay, that they are working proper or not. Okay, so this is my input A, and this is my B, and this is my output Y of the NAND gate. Okay, Harshvardhan, is it coming from your side? That's how it is it giving metal one vertically when you are selecting metal to the current paths? No, it's been using metal two only. The colors are quite same. I mean, quite matching. One is a little light and a little dark. So they look almost the same, but they are of different layers. Okay, they are different layers for sure. So let me assign any input to it. So I take a square clock and assign to this IO pad this time, and I call it at A. Let it be 1 and 1 nanosecond. I just change colors for a faster load up. I take a clock, apply it to this node, call it B. Let it be 2 nanoseconds, and this is the node I want to see and observe. So let it be Y. That's it. And let's simulate. Ooh, what happens? It's not working. It's not working. I double click on the input. I make it slower, 8 times. And this has to be 16 times. Okay. So I make the clocks very slow. Now it seems to a little bit work. You remember the concept of the delays, the capacitance delays? Okay, you remember that, I believe so, right? And here the output is not coming, so I make it more slower, 32 and by 16. Okay, the huge signals. And even I increase the step size to make a faster run of 0.5 maybe. I just go till 100. So yeah, this is how it charges and discharges, and probably it's not even doing that performance. So what happens? Your NAND gate is so small, so small that he's not able to charge that capacitive metal layer of that IO pad. He was too small, too small. Okay. So as they were metal layers, 1, 2, 3, 4, 5, 6, I mean like 6 metal layers on top of each other, and big IO pads, as you know, compared to the size of the NAND gate you're using, they're so stacked. So he's not able to drive it. Okay. He simply cannot. And then your design will be disaster. Okay. So they won't work. They work on the simulations, but as you connect IO pads, things becomes complicated. Okay. So this is why most of the chip designs, when they have to drive heavy load, they use stage ratio inverters. Okay, staged. I just share it. Okay, I believe you are seeing my screen. Something like this. Are you able to see this figure? Guys, are you able to see this figure? Hello. Great.
Yeah, we are able to see. Continue.
Yes, okay, great. Okay, so this is a stage ratio inverter design. So in anywhere you have an heavy load to be driven, so what you do is you make a big inverter. You make a big inverter to drive that load, which has a huge amount of current. But what will happen as this inverter, like the G4 inverter, that will be huge in size. So the input gate capacitance of this inverter will also increase, because that's a big W by L ratio. There's a big W, and as the W increases, the capacitance also increases, the input gate capacitance. Okay, and so G3 also needs to be bigger one. So that's what you do. I mean, like you make and G3, which is a little smaller, to drive the G4, and as the G3 input capacitance also is higher, you make a little smaller G2 and then G1. So in the end, the input gate capacitance of this buffer design would be very small, because the someone who is driving G1, he has to face very small load. Okay, so he will face a less capacitance, and hence he would be able to charge and discharge G1 quick and faster enough. And G1 can drive G2, G2 can drive G3, and henceforth. And G4 can drive the highest amount of load. So this is how, you know, you try to increase the torque, okay, at some expense of delay. Definitely there would be a delay involved, but somewhere, somehow, some compensation has to be made. Okay. So let's see that is this logic correct or not. Okay. Can anyone tell me the 74 series ICs for the inverter? Have you guys used it? 74XC.
04 7404.
That's good. Not the images. We go to the, okay, let me say the Texan instruments. So this is the data sheet from Texas Instruments of their hex inverter. It has 6 inverters. So let's download and see how do they make. So this is a logic diagram, okay? That you give A and output Y you will get. Okay, understood. So I just scroll. Did they mention somewhere? Okay. Although they are doing it, but they're not mentioning it. Okay, it was not here. Let me check from another company. So this is from Nexteria. This is also an chip maker. Yeah, here we are. They are doing it. So this is, they mentioned that, sorry for my zooming too much. Yeah. Okay. So this is what they mentioned, that we have 6 inverters inside, and this is the logic symbol. So that logically, this is how the entire IC pinout will be symbolized. And this is the IC International Standard Format symbol. And then he tells that this is the logic diagram, that one inverter, this is how one inverter is made up of. So one inverter is made up of 3-staged inverter. Okay. Although they are not mentioning the size also, that the big, small, medium, and the small. No, they are not doing that way. But at least they are mentioning that there is a 3-stage inverter. Okay. And this is it. So this final one is a big inverter who can drive a big IO pad. The medium one can drive the bigger one, and the smaller one would be the input gate capacitance, would be small. Okay. So this is what they don't mention anything on the IO pad. Definitely not, because this is not the gate level data sheet. This is not that one. This has all data sheet with the IO delays. Okay. So here they mentioned the how much amount of capacitance, etc. it can face. Okay. So this is a power consumption capacitance, power dissipation per capacitance. This is 24 picofarad. Okay. So these are the power consumption, etc. has been mentioned. Okay. So this IO pad you can explore during your end session. Okay, you guys can do at your places tonight. You can just explore this IO pad and design something and see that how does it comes up. Okay. Okay. So then we move on to another simple experiment, which is a common drain amplifier. Yes, 64. Wow. Okay, good. So we make a common drain amplifier for our today's classroom work. Okay. Last time we did common drain amplifier. Okay. So do we have wiki page somewhere? Yeah, I think this is the wiki page. No. So generally in common drain, okay, you have, and you can use an NMOS or a PMOS. Okay, generally an NMOS used, and high resistance, which is used to for the pull down. Okay. Do we have this? No, this is only formula and given this thing. Source follower. Okay. You guys have done this earlier in your class work, in your classrooms. Common drain. Sorry. Yes, guys, have you done this earlier, or this is yet to be covered? Okay, great. So I just open this up. Just a second. I just open that file, which I would be having it. Okay.
One more thing, as a student, no, usually they'll never see the data sheets of any of the devices. See, in the colleges also, what they do actually, see, even the college, the blue book, they said, no, the teacher says that, these are the component to be used for experiment. Just they'll use it. See, even if it is a 555C or 7404 or any of the devices, they'll never go through any of the data sheets.
Okay, but generally for 74 series they should, right?
Yeah,
I think
any of the circuit, before going to the circuit, they should refer to the data sheets. It's available free of
right.
cost from the companies. They should go
Yes.
through it. See, in earlier
Ah,
days, actually, we used to go and request the manufacturer to get the data books. Now, actually,
okay.
everything is available digitally.
Yes. And earlier we used to keep books.
Yeah.
There were data sheet books available from Texas Instruments and NXT, all that one companies.
Yeah, I have
They
full
used to
set of.
courier even. Even the Xalis also, they used to send all this courier method, CD based.
Correct.
The internet has brought many things in our hand. We don't value that much now. Anyhow, okay. So let's, today the time is remaining short. So we just covered this common drain. So this is like having like a large, basically, it's not right. Yeah. So you can have an NMOS driver, which is driving this, and we can have a resistance, which is a very high resistance. This is like generally a low resistance. Okay. And here we have output. Okay, so this is a common drain because the output goes out from the source, and that's why the drain is remaining, and that's why it's a common drain. Now here, this resistance, instead of this making a virtual resistance based resistor, what we will do is that we will make an MOS, okay, and we'll drive it through a VDD, and we will make another MOS, okay, and that will have this value connected over here, and here the length would be very large. Okay, so because we need to have very high resistance, right? So a very less amount of current should be able to follow through the output. So this is the design we will make, and this is BO, and we'll put a small, Shagunwala capacitor at the output. Okay, so let's make this, okay, and see that how the runs. Okay. Yeah. So let's design this. So I use 45 meters. So is it better? I want now disable my video because I will be only showing this. I hope now the audio is better. Better? Can you give information? Then only I proceed. Is it better? Okay, if you guys confirm, then I proceed the experiments. Sorry, connect. Looks like it's a
Yeah, now you can share
lot
it.
of break day for me. Yeah. Okay. So I proceed making drain. You guys can follow through again later in your sessions, in your classrooms. Um, so this is what we are going to make. I just show you here. We'll use MOS, okay, for the amplification purpose, and this is load resistance, but it have a very large thing, so it can have a resistance, okay, and that will allow a little more amplification. Okay, so we go to the layout. I believe everyone is okay.
Sir, your screen is not visible.
Okay. Is screen visible?
Oh yes, sir. Now it is visible, sir.
Okay, sorry, I'm apologize for this here, but I can't help because can't commit on the Wi-Fi network how they perform. Yeah. So let me make this one. So I just use a MOS transistor. So first of all, I make a large resistance in MOS. So I can click from micron base anything. So I say micron, which is the default value. So I just say it's in 0.5 micrometer, and only 1 micrometer is too much. 0.5 is good. So 0.5 micrometer will give me 0.013 milliampere of current. So that's a quite a small amount of current. So here you can see that NMOS has a very large length. The width is now wide. Now I will go to modulator again, click on NMOS, and now I will have a large length NMOS. So I'd say maybe 0.5 micrometer. So this will give me 0.4 milliampere of current. Maybe I can just say 0.8 milliampere. No, okay. And I just place on the side of this somewhere over here. Okay. And now I will just direct to possibilize it. So I just take a VD supply, and that'll be for the NMOS, one of the terminal on the left hand side. And I'll take and ground the bottom NMOS right hand side terminal. So both are biased of this power supply. Then I take the stack clock, apply to the gate of the first inverter, and make the same standard my 1 nanosecond low and high. Okay. Now I just connect the output metal one of this node. Okay. Oh yeah, just right click, connect layers. Okay, and the same metal one is connected to this terminal also. So I short this one. Yeah. Okay. And this is my node output. So I take a visible node and connect it over here and call it as V out. Clock 1, I just rename as V in because that's what my wanted. And I take a small capacitor and place on the output node, a very small, like 0.01, very small capacitor. And the colors, and I believe I've done all. Yeah, working in the shot. Okay. So first of all, go to voltage versus voltage curve. Okay, and then you see a positive slope of this. Okay, this is a positive supply because it's not inverting. It's not inverting one. So I can see a crossover. So crossover is around 0.925. Okay, so that's okay. I just remember this. And the slope is around 0.6. So the gain is, instead of going on the positive side, it's very less. It's 0.6. But that's okay. We'll find it out how to improvise this gain setting. Okay. So if I double click on V in and I go to 500 megahertz and maybe of 0.1 and offset at 0.9, because that's what the offset I saw. Okay, and I simulate this. So it was 0.925, but that's okay. So here you can see that it becomes that common drain, like following amplifier. So it's following the input. The only thing is that the amplitude is less than the input because the gain is 0.6. So the output voltage is equal to 0.6 multiplied by the V in. So that's okay because that's how the design works. Okay. So now maybe I just try to increase gain or change the gain values. And so let me stretch move. So what I do is just stretch this up. Okay, I increase the length. So you can see that I've just shifted the diffusion and all this. Okay. So what I do is take the diffusion and I draw n diffusion and draw a box and join them. So what has happened? They have reached. At the same time, I can take the stretch move and click on the left line and extend it just before the metal line. Okay, maybe one step more. Okay. Maybe this delay again. So what then I've increased the length of the bottom NMOS. So that will give me what changes. So I the cross voltage slightly changed, and the gain has not much been affected. It's 0.6 only. There's nothing much of change as of now. Okay. The next part. What happens if the width of the common drained MOSFET? So what impact will bring? So what I do is I just copy paste. I just copy, okay, this entire NMOS part and place on top of this, somewhere like this. Okay. So what I done here is just increase the copy the diffusion. I just extend the diffusion back and join the bottom. Okay. Then I just make another one gate, maybe gate, and extend it on the top side. Okay, now the metal layers, it's not necessary, it's good to have it if you want, if you are making it good, otherwise you can leave also. Okay, this is something that I just no, it's still so we have to find a method how and before okay. And I just open it plugin. Okay. So this contain what we on the books. I believe you guys have seen that hello, hello.
Yeah, you can continue.
Yes, sir.
Yes, sir. Okay. So as you can see, even on the books which is there, because this is just used for current gain, and if you see the voltage gain, generally is a 1. So we have reached 0.6. So that's close enough. So the maximum you can reach is 1 because that's what it's being used for. Generally, it's for more of current gain. Okay, it more or less looks like the current mirror circuit only. Okay, so generally this is what you can achieve from a common drain amplifier. Okay, so that's why it is also called as source follower. Okay, and that's it. So what you guys can today you do in this, you just make this common drain amplifier at your place and see that what kind of values of the gain you get. Ideally, it should generally we have achieved somewhere around 0.6 to 0.8 at the max, nothing more than that. Okay, because this is how it works. And secondly, you can just explore the IO pads, try to make the IO pads on your own and see that what kind of IO pads you can make uh, to connect your design. And I'm sure you guys will come across many obstacles in making IO pads. So just try to retain them and read about IO pads. And tomorrow we can little bit discuss on IO pads. And maybe I'll just show you this ADC example. Okay, and how does it works? Because the ADC which is there, this is a very big example. So we would be able to only do the steady casing of the ADC. Even I mean, just to open and explain the ADC itself may take a significant amount of time. So I'm reserving for the later stage so that jitna, at the max possible, you guys are familiar with the software tool and the design process. Then I thought to cover the ADC part. Okay. So any doubts, questions you guys have? So I just keep the last few minutes for the questions and doubts. Okay, it's still breaking the voice. I'm so sorry, guys. Today the internet has been troubling a lot. Although my home internet is back, but I'm scared to switch the net. I'm not sure how well it is working. Okay. So let's keep few minutes to talk and discuss. If you guys have any questions from anywhere, I said when this COVID is going back, I can try to answer as many number of questions. Guys, ladies. Oh, yes. Okay. Yes, we can repeat this common drain tomorrow. I do one thing, I just save this file and share it with you guys so that in case you wish to open this file and see this. Okay. So I'm just sharing this and any questions from your side?
Let them store that what are the example programs you given?
Yes, I have shared. I mean, every day, whatever the classwork are there, I just share with the students.
Yeah.
Yeah, maybe I can just share a few more, which are for the reference purpose.
Students, have you worked in any other tool earlier? If you worked, just say in the chat box yes, and the tool name, Cadence. Okay. Anybody else? How easy this microwind compared to Cadence? Swati, can you come on audio?
Yes, sir. Sir, cadence is like a very long process of designing, sir.
That's correct. Yeah.
So I felt this was like, yeah, like, yeah, like it's easier than cadence, sir. So
See, earlier what happened, many colleges, they were using this microwind tool. In fact, in Karnataka itself, the 69 engineering college, they were using it. But later, because of the misconception of using cadence tool is as it is, it is an industrial tool. So many colleges they procured cadence tool, but unfortunately the faculties were not ready enough to give a training on cadence tool. So in fact, actually they failed on a higher end tool and as well as the lower end tool. They didn't use it itself. So because of that, many students who wants to work in the VLSI field, they could not learn the full process. So now you can tell your faculties also that how easy this microvent tool, because next week onwards actually we are going to do some faculty development program on the same tool for some colleges, because some colleges they came back and they told actually, see, if you can give me training and definitely will reuse that microvent tool. See, in fact, you will not believe it, cadence tool was around 4 to 5 lakhs rupees for every 3 years. Now because they feel that actually there is no competition, they are raised to price to 10 lakhs, and many college managements they are not able to afford that price. So in fact, you can go and recommend your faculties also, so that your learning process will become easy and also you'll learn better.
Yes, sir.
You are from which college?
Sir, I'm from GSSS, sir.
GSSS, okay. Parmachari.
Sir, no, sir. I'm from EC department, sir.
Okay. Who's HOD now?
Sir, Rajendra Patil, sir.
Rajendra Patil, okay. In fact, GSSS also is my customer, but unfortunately they stopped using it. But internally, some colleges they are using it without our permission.
Sir, actually we work using GPDK 180 nanometer technology, sir, like for 7 semester.
Okay.
In cadence tool, we use GPDK 180, sir.
But have you completed your process?
Sir?
Full
Sir?
flow you complete. I mean, you learned full flow.
Yes, sir. Like
Okay, good.
till the parasitic capacitance extraction we have learned, sir.
Okay. Same experiments you can try in this.
Okay, sir.
Now Shivkumar sir is the principal, right?
Yes, sir.
Okay.
Yes.
And when you joined, Satyanarayana sir also was HOD of ESE?
Yes, sir. I was in first year, sir. So
Okay,
he
MV
retired
Satyanarayana.
that time. Yes, sir.
Yeah, correct. MV Satyanarayana, he was in MC Asan as a professor of ENC and as well as a principal. Again, we supplied microvent tool to MC Asan also. In fact, till today, MC is using microvent tool. Even recently, they updated the software also.
Okay, sir.
Okay, that's all today.
Yes, sir.
Okay.
We catch up again tomorrow, and we start a little quick because tomorrow would be probably I would expect a lot of questions from the students. If there's something, I'm thinking of keeping some 20-15 minutes for interaction.